Good afternoon, everybody. Welcome to this session on particles, droplets, and bubbles. Particles and droplets are very relevant to us right now, one of the reasons why we're remote today. So without any further ado, I'd like to invite our first speaker, Patrick Holland, to share his screen and share with us his work.
Thank you for the nice introduction. Okay. Thank you for the nice introduction. The last two OpenFOAM workshops I was also presenting, but that time I was more talking about cuttings transport connected with fluid structure interaction. In today's talk, I will focus solely on particle transport, but this time not in Newtonian fluids, but in viscoelastic fluids. I would also like to thank my co-authors, Mr. Roger Aragal from BKU and Joachim Oppelt, also from Clausthal University. And for my outline today, I will give you a short motivation again. Then I will talk about the simulation setup that I'm planning to use when validating or when testing my code. And then I would talk about the challenges which I've been facing this time in my work. And lastly, I would talk about the parameters for the simulation study and finish the presentation by some final conclusions and a brief outlook on future work. For the motivation, I'm still working in the oil and gas industry, or the focus area, application area is there. And there we are still drilling, and drilling is important because most energy resources are located far below the surface. And the drilling itself is, especially for geothermal projects, a very large cost driver. So, and as part of the construction, it's also important to clean the wellbore well from the generated cuttings. And that takes generally quite a lot of time. So if we could optimize that cuttings transport, then we could make geothermal energy more economically feasible, and also hopefully it would be more widespread. But as also before, we are in a very challenging environment. We are very far below the surface of the Earth, so in situ measurements are still difficult. So mostly we need to rely for the research on physical and data-driven models. And this time I will become a bit more realistic in that sense that this time I'm using fluids with viscoelastic characteristics, which is also rather common in the drilling field, unlike Newtonian fluids, which I was presenting in the last 2 years. For software setup, I'm this time using OpenFOAM and not the fork foam extend. So I use the original setup. Again, lights is coupled via CFDM coupling. And this time I want to focus a bit more on the fact that what is inside CFDM coupling. Actually, it consists of many different models, which are, I would say, unified in one framework. There is a model for the location, for the data exchange, for the mesh motion, but also for the forces. And this is what I would like to focus on today, on the force models, because this is where the work I'm presenting today is located. For the particle forces, as before, the forces between the particles and the wall, and the particles and the drill pipe are considered for the simulation setup. For the geometry, the things have changed a bit. We have now the inner pipe throughout the whole simulation area, but we still have also particles and the fluid, of course, in the annulus. And this time we also use a periodic boundary condition for the flow. But apart from that, things are similar. The inner pipe is rotating. We have the flow and the particles. So which challenges did I face when I started working on it? First of all, CFDM coupling did not include any force models for viscoplastic fluids. Then also, while implementing the models we selected, I also noticed that there was some lack of functionality, which I had to fix. And of course, the last challenge, as always, if you make a new code, you also need to validate it. For the force models, we decided to use the work by Ashkik, which was published in 2016. And from this paper, we derived 3 new force models. The Ashkik drag model, which models both drag force and hydrodynamic torques, and the 2 lift models called Magnus lift model and Suffman lift model. And for the validation, we follow the same procedure as mentioned in the base paper, and this is based on experimental data reported by Tom Wren et al. In 1986. Here, I also briefly want to show you how this model looks like. The most important part are the calculations on the following slides. For the Ashkik drag model, we use the Reynolds number for power law fluids, the Bingham number for Herschel-Bulkley fluids. From that, we calculate the Reynolds number for Herschel-Bulkley fluids, and then consecutively, we get here at the end our total drag force. A similar procedure is also following here for the hydrodynamic torques, but there is something different. We also calculate our omega, the rotational Reynolds number, but we cannot do the data transfer like we did for the drag force, because this was not included in the base class of the CFDM cloud. So this is why here at the bottom, we have this additional line, which is making the data transfer manually. For the Magnus lift force, things are fairly similar. We also calculate the lift and return it via the CFDM cloud model object, and similarly also for the Suffman lift model. So just to talk a bit more about the lack of functionality, CFDM coupling considers both the general case and the immersed boundary method. The hydrodynamic torques are part of the subclass or derived class for the immersed boundary method, but not for the general case. So, and those are just virtual methods and attributes in the base class. So I had to somehow work around this, and that's why I implemented the separate variables in the force models and not up, so to speak, in the general object. For simulation study, we want to use the simulation parameters as mentioned here. It's a 12-meter long section, and in addition to the parameters shown here, also the friction coefficients are modified. And then we will also do there a big simulation study and hope we will get comparable results compared to Tom Wren and Ashkik. That brings me to the end of my talk. We have implemented those models. We are right now in the validation for the laminar flow. And for future work, we also hope that we can do some validation for the turbulent region, but for that we don't have, I guess we would also need additional code, which we don't have right now. With that, I would just like to briefly show you, for sake of completeness, the references which we used in our work. The first 2 are for CFDM coupling and lights, and the second 2 are where we take the data from and the equations from. With that, I would like to thank you for attending, the organizers for giving me the opportunity to speak today, and you for attending this talk. And now I would be happy to answer questions.
Thank you, Patrick. So we have a question from Richard Kenny, who's asking, which version of OpenFOAM did you use? CFDEM v 3.8 seems to stop at OF 3.0 and OF ESI 1806. So there's some software compatibility issues there.
I would say it's not 3.0x, it's 5.0x where they stopped. And that's also the version which I'm using here in this study.
Okay, and was that lack of functionality that you experienced due to the kind of the stopping of development of CFDEM?
The lack of functionality is more or less, I think, based on the fact that for the general case, they don't consider particle movements, rotation. They don't consider the rotation of particles. So that is the reason why I had to implement it.
And if there's any more questions want to come through, I'll just ask one while we wait. You're talking about the validation work. So can you just give a bit more detail on how you plan to validate, and what kind of data you have to validate against?
That the data to validate against, that is data by Tomren, which did a quite extensive experimental study in 1986 and published the data, and we want to validate against their data. So it's just publicly available data.
What kind of what kind of measurements do they perform?
They did measurement profile, velocity profiles, and I think also they did some tests about the particle concentrations.
Very good. So a very rich data set to compare against.
Yeah.
Fantastic. So we'll just wait maybe if there's one more question. If not, then we can move on. We can obviously thank our speaker. Thank you, Patrick, very much. And we will just check how many questions. No more questions. We'll move on to our next speaker. So thank you very much, Patrick, for an interesting talk. Our next speaker is Josh Williams. Josh, as soon as you're ready, there's no rush. We're ahead of schedule.
Great. I'll just share my screen. Thanks, Kevin.
Thank you.
So you can see this and hear me okay?
Can indeed.
Right, so thanks, I'll just get started. Hi everyone, my name's Josh Williams. I'm going to talk today about my work where we've been modelling turbulent dispersion in dilute particle-laden flows. So currently respiratory disease such as asthma affects over 1 billion people worldwide, and these diseases are mainly treated with inhaled drugs. But the problem is that the drug deposition is known to vary quite dramatically across different patients. So CFD modelling is an emerging tool to predict how drugs deposit in patients' airways. But the complex geometry, particularly in the upper airways, like we can see here, taken from CT scans, can create complex flow structures such as recirculation and secondary flows. So unfortunately, we can't resolve all model the smaller scales, which will influence how the drug, or our prediction of drug deposition. So there has been some work done modelling turbulent dispersion, particularly these two really good review papers, but not much has been done in complex geometry like patient airways. This is what we wanted to evaluate, how important these models are in this setting. But first, to do that, and what I'm going to talk about today, we had to implement a turbulent dispersion model, and then we validate it in channel flow. So in our modelling framework, we solve the filtered mass momentum continuity equations on a fixed grid, like so, and track point particles as they move throughout the domain. So you can see that mass continuity depends only on the divergence of the velocity field. So this, and there's no contribution of the particle volume fraction. This means that the fluid is one-way coupled to the particles. Then momentum continuity depends on the pressure gradient and resolved viscous stresses, as well as these subgrid stresses, which we model like this. So here, nu SGS and k SGS are the subgrid viscosity and turbulent kinetic energy, respectively. S is the resolved strain rate, and delta is the Kronecker delta. So we get nu and k with the dynamic k equation model, which is already available in OpenFOAM. So to model turbulent dispersion using the available OpenFOAM framework, we would solve Newton's equations of motion, accounting only for drag in the channel flow, where drag depends on the density ratio, particle diameter, divided by the drag coefficient and the magnitude of relative velocity. So here the relative velocity depends on, of course, the particle velocity UP, the fluid velocity UF, which is interpolated to the particle position, as well as some fluctuating term. So in OpenFOAM, based on the turbulent kinetic energy and some random variable sampled from a normal distribution.
We appear to have lost Josh's audio. Just give him a second and see if you can reconnect. We appear to have lost Josh. We're ahead of schedule, so let's give him a moment to reconnect, and then we'll see if we can continue from where he left off. Please bear with us. Okay, Josh is back.
Hi, sorry, I think I cut out there. My Wi-Fi is not so good.
Yeah, no, we lost your audio for a second. That's okay, but please try and continue. Thank you.
Yeah. So did it cut out at this part?
Yes, you were just discussing that, yeah.
Yeah, so we use this Innocenti model with some extra terms from Clausic. So one of these extra terms is to account for diffusion in space here with square root 2 times the kinematic viscosity, where this parameter dW is a stochastic Wiener process, which is just a vector of random variables sampled from a normal distribution. Then in the drag term, we have this new parameter US, which
unfortunately, Josh appears to be disconnecting again. This is always a problem with an online event. I had some significant disconnects myself yesterday, so hopefully we can continue soon. Perhaps we can move to the next speaker, and if Josh can stabilize his connection, we can have him speak at the end. That sounds reasonable.
Okay, should I share my screen?
Yes, so please, Jenna, thank you very much. So we're going to move to our next speaker, and we'll get back to Josh as soon as we can. Thank you.
Okay, so my name is Elena Machak. I'm a PhD student. I work at DCS Computing, which is a company that owns CRDM coupling, which was already mentioned today. My supervisor is Christoph Ganiva and Stefan Radl, and I'm interested in high temperature processes. By high temperatures, I mean above 400 degrees Celsius, where we have radiation as an important mechanism of heat transfer. And today I'm going to show how we use a P1 model to model radiation between particles. In first part, I'm going to try to explain what exactly makes radiation challenging. In second part, I'm going to contradict myself and show how actually it can be quite simple, as P1 is one of the simplest radiation models there are. And in third part, I'm going to show some simulations. So first, radiation is complicated. When it comes to radiation, we have three parts. We have absorption, emission, and scattering. Absorption and emission are pretty straightforward. Absorption is the radiation that gets transformed into internal energy. Emission is the opposite, internal energy that gets transformed into radiation. And scattering is actually what makes things complicated. The mechanism of scattering does not participate in the energy exchange, but it does deflect the radiative beam from its original direction onto some other. And the way it is depicted here, it's highly directional. It happens at a definite angle. In nature and in industry, we more often encounter particles that will scatter radiation in all directions with varying degrees of efficiency. For example, water droplets that comprise clouds, they tend to scatter radiation diffusely, mostly in forward direction, while air, air molecules, which are much smaller than the wavelength of the sunlight, they tend to scatter radiation both in a backward and forward direction, and most efficiently in the blue spectrum, which is the reason why we see the blue sky. So when it comes to DM modeling, there are different ways how to calculate this radiative heat transfer between two or more particles. First method is Monte Carlo ray tracing, which is very precise, but very cumbersome when it comes to computational times. So in this method, at every time step from every particle, ray shoots in a random direction. And then we follow the ray as it moves throughout the domain and calculate the radiative transport equation for the ray. And so as you can imagine, this is limited only to a few particles because it would be impossible to calculate setups which we encounter, for example, in industry. Another method is view factor calculation, where a particle is represented by a collection of dots. And for each of these dots, we calculate how much the dot illuminates the particles which surround. So this is also, it also features a lot of additional calculations. However, it doesn't have to be that complicated, because if we look at the actual applications, we see that particles tend to appear in bulks. So in packed and fluidized beds, in rotary kilns, in selective laser sintering and other applications, we always have particles that are in close proximity to each other. So the photons, which carry the radiative heat flux, will not travel too far before being absorbed and reflected by other particles. So it means that all these radiative properties kind of tend to average out. So we can successfully introduce the concept of continuum and view our granular media more in a fluid-like manner. So we are having a CFD cell and we are having Lagrangian particles, and we have this intermediate level where Lagrangian particles are particle cloud which shares average properties, and we conserve the incident radiation at the CFD level, and at the DM level each particle has its own heat flux, which consists of absorbed part of the incident radiation and the emitted part of each particle. At the CFD level, when it comes to radiative properties, we sum up influences from the fluid and the particles. And at the whole level, we solve one very simple Lagrangian, Laplacian equation for radiative intensity. Here, we have first verified this model with pure air, because in our setups, we will not always have domains which are completely filled with particles, but rather one part which is filled with particles, another part which is filled with fluid. We have used scattering coefficient for the blue sky, and for this simple setup with two infinite parallel plates, we got nearly perfect agreement with analytic solution for heat flux. Next step, I have sandwiched between hot and cold plate perfect packing of 100 particles, and I have switched up radiative properties for different materials. So I have very opaque particles and very transparent particles. And we have compared the temperature field that settles with the analytic solutions and got fairly good agreement. However, for pure air, things don't look so good when I reach out of 1D to 2D test cases. So for this infinite cavity, we had error in heat flux of 20%. So if we have perpendicular angles, it doesn't work so good as 1D case. However, there is one significant application which is highly one-directional, and it is heat source from a laser. And usually in DM, if we don't calculate the complicated Monte Carlo view factors, we simulate laser heating only by applying a heat source to the upper layer of particles. This is not always good because radiation actually can penetrate further. And here in our P1 approximation, we can see that our heat flux can penetrate further, and we see that it actually resembles what we expect to see in application like that. So here the temperatures that, left side is only radiation, and on the right side we have radiation and conduction. In only radiative heat transfer, we get like very crazy temperatures. This is higher than the surface of sun. If I apply also conduction, I see much more uniform profiles. But the excess energy is, of course, in such an application would, of course, go into phase change. So to get any conclusive comments about using P1, I would have to include much more physics than I have right now. So yeah, that's all. Thank you so much.
Just waiting for some questions to come through. If anybody wants to ask a question, please use the Q&A section. Yeah, it's very, very interesting work. You mentioned at the start with the Monte Carlo ray tracing is quite expensive. Do you think this is becoming less the case now that we're seeing dedicated ray tracing hardware become available for numerical modeling?
I'm not sure. I cannot really comment too much on ray tracing because I'm more inclined towards these CFD MDM. So I'm always trying to look at it from a CFD perspective. Yeah. However, we have very early decided not to do ray tracing because it's what we have right now. It's really not feasible to apply to any type of simulation setup that we would encounter in industry, because we have like more than 20,000 particles, and this was very, very, very slow. So we have implementation of Monte Carlo ray tracing, but it's not really feasible for industrial context.
Indeed, and then what you have appears to work quite well. So we have a question from Faraz asking, did you consider heat transfer between particles due to particle-particle collision?
Do the particle-particle? Not yet.
Not yet.
I don't think actually that we will going to. I mean, there is due to particle. I mean, there is conduction between particles. If that is that, I'm not sure if there is something special when particle collision happens. In my entire work, I'm mostly focused on radiation, which is radiation from a source, radiation from boundaries, from walls, and radiation, of course, between particles.
Yep, very good. Philip Cardiff is asking, would it be possible to include particle melting to simulate laser beam powder bed fusion?
Of course. I mean, to really make this, how to say, useful, we would need to, of course, include melting, because as I showed in the example, If we don't include melting, the temperatures go too higher than it would be in nature. So yeah, the next step would be to couple it together with melting with phase change.
So Patrick Holm obviously asks a very relevant question, and on that, how are the melted particles then treated? What's your approach to melting the particles?
I'm not working on melting particles, so I'm mostly concerned with just radiation. So that's part. So unfortunately, I cannot really say too much about melting itself.
Is that something that is on the horizon?
No, not for me. Not for me. So maybe I will. Maybe I don't know. But it's not the focal point of my work. I'm more. Yeah, not focal point of my work.
There's already enough to do.
Yeah, there's enough to do.
Changyang asks a similar question, and I think you've answered that. There's a question about particle melting. So there's a lot of interest in particle melting. So it's clearly a hot topic. Excuse the pun. So we'll move on to our next speaker, and thank you, Janela, very much.
Thank you.
So Cello is our next speaker, and then at the end, Josh will get you back in again. Hopefully your connection is stable.
Hi, Kevin, thank you. I will share my presentation now.
Thank you.
And thank you. I will start it. So my name is Célio Fernandes, and this work is entitled CFD Modeling of Particle-Laden Viscoelastic Flows in Hydraulic Fracturing Operations. I'm working at the Institute of Polymers and Composites in the Department of Polymer Engineering in the University of Minho, Portugal. This work was done in collaboration with Salah Farouji from the Petroland company in USA, and the former master student Ricardo Ribeiro, and an actual researcher at the Institute, Ana Isabel Roriz, and with the guidance of Professor Gareth McKinley from the Massachusetts Institute of Technology. So the outline for the presentation is the following. First, I will introduce and give the motivation for this work. Second, I will describe the numerical approach we employed. In the third place, I will describe some direct numerical simulations we perform to derive a derived model. And then in the fourth and fifth section, I will present you two different case studies to validate the derived model that we developed in a Eulerian Lagrangian solver. These case studies will be the annular flow and the rectangular channel flow. Finally, I will address the conclusions of this work. As the first presenter explained, the process of the hydraulic fracturing is a process where we have a very high energy consumption, and the dispersion, the disposal of waste is also very high. Here we want to optimize the way the oil and the gas is extracted from the soil, and usually what happens is that a fluid is injected in the conduct, and the fluid has also sand particles in its matrix. So usually we consider a suspension of a fluid and a gas. Normally this suspension is characterized with a Newtonian fluid, but we want to understand how the elasticity can change the behavior of this process. The first theoretical results that we have from the literature is from Stokes, where he derived the sedimentation velocity of a particle, and this can be very well validated in detailed and fully resolved solvers. But the purpose here is to simulate an industrial case study where millions of particles are injected in the conduct. So we want to change our perspective from the resolved CFD-DEM method to the unresolved CFD-DEM method. Here on this last one, the particle's diameter will be lower than the grid cell size. And with these methods, we can handle millions of particles and the contact between them too. For more detailed information in these two different methods, you can see our publications in Granular Matter and Journal of Non-Newtonian Fluid Mechanics, where we validated these two different algorithms. But for this study here that I'm presenting, we want to consider complex suspensions where the fluid has a viscoelastic character. And here we will consider the Oldroyd B constitutive equation to calculate the polymeric stress tensor, sigma p. And also, as I referred, we consider the particle's diameter lesser than the grid cell size. But for the viscoelastic suspensions, we need to know drag force expression or a closure model for the drag which the fluid exerts on this in these particles. And also we need to take into account the presence of the other particles in the system. So for this purpose, we conduct direct numerical simulations considering different kinematic conditions. So first we will consider only creeping flow conditions where the Reynolds number is lesser than 1, but we consider that in our system we can get a volume fraction of particles which range between 0 and 20%. Okay, and we then measure the average drag force that we represent by in brackets and an F, uppercase F. And here on this plot, we can see the numerical results that we obtained with the blue symbols here from 4, 8, 12, 16, and 20% of particles. And we compare our results that we obtain with a finite volume solver with the results from Hill et al., which were computed with a lattice-Boltzmann method. Okay, and also we compare with several closure laws in the literature for the Newtonian fluid. We see that we are with results very similar to the lattice-Boltzmann results from Hill and with the results from the literature. But we keep in mind that the most recent results in the literature was given by Van der Hoff, and the Van der Hoff drag force model is given here on the bottom. This will be an expression that we will extend for the viscoelastic fluids. So for the viscoelastic calculations, we consider the retardation ratio beta equals 0.5, the creeping flow conditions as before, and the Weissenberg number, which measures the elasticity of the fluid, was varied between 0 and 4. Again, the volume fraction of the particles varied between 0 and 20%. Here on the graphic on the right, I present the results that we obtained for the different Weissenberg numbers and the different volume fractions. And as you can see, the effect of the Weissenberg number is very, very small. And if we consider a fit of our numerical results accordingly with the Van der Hoff model, we can get a fit with a square regression factor of 0.98% and only 5.7% of average error between our numerical results and the fit. So next step was to implement this drag model, which works for viscoelastic fluids in a Eulerian Lagrangian solver in OpenFOAM, which will permit us to do the simulation of particle-laden fluids with viscoelastic fluids and with a large amount of particles. This solver was then validated in two different case studies. The case study one is the annular flow. And here we first considered Newtonian fluid, and we compare our solver, the Eulerian Lagrangian Newtonian solver, with experiments performed by Agatha Robinson in the Schlumberger company in MIT. So we consider this geometry as a proxy for the horizontal well in the hydraulic fracture operation, and the Newtonian oil is considered 10 times more viscous than the water. We consider 1% of particles in the system, which gave us more or less 100,000 particles here immersed in our geometry, and the density ratio is 2.5. You can see here a video of the experimental results you see that the particles are colored with the green color, and we will see that the formation of wings here on in the inner cylinder walls. Okay, and in the end of the video, you will see that the wings are the only zones where we have some convection of particles, and we have a sedimentation height here on the bottom. We validate our numerical algorithm for Newtonian fluids with the same case, and here you can see the video of our numerical results with the same configuration. This is a three-dimensional simulation with the 125,000 particles, four-way coupled. So we take into account particle-particle contacts, and particle influence the fluid, and fluid influence the particles. And again, you can see the wings of particles here, and you see also in a zoom view the particle sedimentation, similar to the experimental apparatus. Next, we move to the viscoelastic fluids to validate our solver. And here we perform simulations for the dimensional number called elasticity number, which is the ratio between the Weissenberg and the Reynolds number. And we consider a low and high elasticity number. We see that here the distribution of particles in the top graph plots, and the distribution of the fluid velocity on the bottom ones. You see that when you increase a lot the elasticity, it seems that the mass of particles is lesser, which means that elasticity can play a major role in the sedimentation of the particles. Then we proceed with a rectangular channel flow geometry, and here it is known that it is very important for the propant suspension flows. And you can see the paper from Meeker et al. In 2020, where he studied the propant transport in a Newtonian fluid. We first validated our solver with Newtonian fluid, and then we went to the viscoelastic one. So first, we consider only fluid in the rectangular channel, and we measure the pressure drop in the channel for different inlet flow rates. It is known from the literature that the Hagen-Poiseuille pressure drop is given by this analytical formula, and our results, which are plotted at red color, match perfectly the analytical solution. Then we insert also propant particles in the Newtonian fluid, and we measure the sedimentation height of the particles during the steady state sediments under flow, and when we stop the insertion of particles, we also measure the static sediment height once the suspension flow was ceased. This is represented by H and H0 respectively. So we see that for the three different volume fractions that we tested, 2.5, 3.8, and 5%, our numerical results almost match perfectly for all cases the experimental ones. Next, we consider the viscoelastic fluid, and again, we set the elasticity number equals to 30, which is a high elasticity number, where we can see the effects of the elasticity of the material. Here we see some distribution of the particles in the top and the fluid velocities at the bottom at the 2/3 length of the channel. You can see that there is a big difference between the Newtonian case elasticity 0 and the case where we have higher elasticity. See that in the Newtonian fluid, the particles tend to sediment in the channel, but in the viscoelastic case, you see that the particles are more uniformly distributed in the channel, and the layer of particle sedimentation is very thin. This can help the process of hydraulic fracturing in the hydraulic fracturing operations to have lesser dispersion of wastes in the system. So in the conclusions, we have performed direct numerical simulations of random arrays of spherical particles immersed in Newtonian and viscoelastic liquids using a finite volume method. We could be able to approximate a closed form model for the drag force in all droid B viscoelastic fluids for creeping flow conditions, a retardation ratio of 0.5, Weissenberg number between 0 and 4, and particle volume fraction between 0 and 20%. Then this drag force model was implemented inside an Eulerian Lagrangian solver, which can handle particle-laden viscoelastic flows. And finally, as a proof of concept, this newly developed solver was assessed for horizontal wells in annular domain and for the proton transport sedimentation in a channel of rectangular cross-section. My knowledge goes to the MIT exploratory project from the Portuguese Foundation for Science and Technology, and also for the search cluster in the University of Minho, the Texas Advanced Computing Clusters in the Texas University at Austin, USA, the Compute Platform in Spain, and the Minho Advanced Computing Center in the University of Minho too. Thank you for your attention, and I'm available for any questions.
Thank you, Celio. We have a couple of questions. Joseph Nage is asking, do you have some stability issues with the Odroid B model? And if yes, what approach do you use to stabilize it?
No, with the drag model that I implement, I did not find any instability. The only problem is if you consider four-way coupling, where you consider particle-particle collisions, you cannot reach a million of cells. Okay, I was able to reach 100,000 cells in the first case, the annular geometry, but for the channel geometry, where I use almost 6 million of cells, I need to relax the system and went to the MPP which is the multiple particle in cell method instead of the DPM foam. Okay, but regarding the drag model, I did not find any instabilities in the system using these let me say the Van der Rohe-like model, okay, which is almost a linear model. If you encounter any, I would say, fraction or a square root, okay, then you need to take any numerical caution with the process, with the implementation. But if you do not have those kind of expressions, you don't need to have any numerical attention.
Okay, thank you. It's interesting. I've been trying to use RioFoam off my own research on microfluidics, and certainly stability can be an issue.
So sorry, can you repeat? I was listening very low.
I've been using the RioFoam.
RioFoam. Okay, but yeah, I did not use RioFoam.
No, I have for my own work. So
yeah, but RioFoam is for the viscoelastic part.
Yes,
it's not
exactly.
for the particle calculation.
Okay. So the next question is then from Zhangyong Li. Do the particles interact with each other?
Yeah, as I explained, yeah, I consider four-way coupling in the annular geometry, and in the rectangular case study, I consider the multi-phase particle in cell methods, which accounts for like a cloud of particles interacting with another cloud of particles, and this is done with statistical methods.
Great.
But always considering the contact of particles and the coupling between fluids and particles and fluids. So this is four-way coupling. I can say that for the annular cylinder, the simulations can take 2 to 3 days. But with the multi-phase methods, they can, with millions of particles in 1 or 2 days, I can get the results. Okay, so I think it's not too much expensive and taking into account that I'm considering viscoelastic fluid and I'm considering four-way coupling.
That's quite impressive. I don't see
yeah, but of course I have the lucky to have a good high-performance computer.
It's always nice. I don't see any further questions, so we have 10 minutes in the session, so we'll let Josh back in so he can finish his talk. Hopefully, Josh doesn't have any connection issues. Thank you, Celio, very much. Appreciate it.
I will stop my sharing.
Thank you.
Thanks, Kevin. Hopefully everything's fixed. Should I start from the beginning or just where it's cut
out? Well, we have 10 minutes in the session, so just in case we get cut off at the end, maybe you can continue around where you left off.
Okay. Yeah, I'll just give you
time for questions at the end.
Yeah. Okay. Great. Yes, so can you see this okay and hear me?
You can indeed.
Yep. So yeah, where I was cut off, so we implemented this new stochastic model where the first two terms are the same as the Navier-Stokes equations. Then because we deal with inertial particles, we have this relative motion term, which depends on the filtered particle velocity and the filtered fluid velocity. We have this stochastic diffusion term, which is based on B, the diffusion matrix, which depends on the subgrid dissipation rate. Then to make sure the stochastic model doesn't drift too far away from the fluid, we have this relaxation term, where G star is essentially just the inverse of the fluid timescale. And we have these new parameters, C naught, which is just a modeling constant set to 2.1. Epsilon SGS is the subgrid dissipation rate. Epsilon tilde is the resolved dissipation rate. And H is the orientation matrix. So we can see that this equation for US follows the classic generalized Langevin equation given by Pope. So for our implementation, we created this new dispersion model class, which has two main functions. The first being it gets the statistics of the Lagrangian phase. So here we get the filtered particle velocity by mass averaging over all particles in a cell. Then it performs integration of the stochastic differential equation, which you do by the scheme that we implemented provided by Minier, where T is the fluid timescale, C is the drift term, so this is the deterministic part of our US model, and then gamma is the stochastic part of the US model. So then we store some extra variables like the interpolated kinetic energy, for example. And finally, we modified the solver to be one-way coupled, and also in a scheme by Minier, they solve for the fluid first and get the particle statistics at the end of the time step. So first we validated on our test case, which has the same setup as these two Marchioli papers. So we've modeled channel flow at Reynolds number 300 based on the shear velocity. We test Stokes numbers 0, 1, and 5, where the Stokes number is just a way to characterize particle inertia. So Stokes number 5, the particle is quite heavy and not perturbed by fluid fluctuations. So our mesh had 64 cells in each direction roughly, which is 4 times coarser than the DNS data. And this gave us a Z plus of 0.5, so we resolved down to the viscous sublayer. And this was all implemented in OpenFOAM 6. So first we compared the fluid phase results against the DNS data, as well as the LES results of the paper whose model we used. So this is the mean velocity across the height of the channel and the velocity fluctuations. So we can see that both LES results agree quite well with the DNS data. However, ours has better agreement at the center of the channel. This is also true for the fluctuations. However, both LES results overshoot the peak of the velocity fluctuation. So a way to check, as a first check that our stochastic model is correct, is that when the particle inertia tends to 0, the particle phase results should just mirror that of the fluid phase. So this is the case for the velocity fluctuations for all LES models. However, for the concentration, where we expect a uniform concentration of 1, because it's an incompressible fluid and mass is uniformly distributed, our US model gives a small error of around 9%. This is compared to LES with no dispersion model, so we just interpolate the fluid, which gives an error of around 20%. And like I mentioned, the Grossman model gives quite bad results for small particles, and this concentration goes all the way up to 18. So it's clearly not suited to our case. So here we compare the inertial particles concentration across the height of the channel. So preferentially, with a larger Stokes number, the particles will migrate towards the wall. So this is known as turbophoresis. And this is captured quite well by both the stochastic models at a Stokes number of 1. However, the LES with no dispersion model just predicts a uniform concentration. That's also true for the Stokes number 5. The Grossman model is around 10 times off the DNS data, and our model was the best performing. It's only around 2.5 times off, although it is still quite a significant underprediction. And finally, we compared the fluctuations in the particle velocity. So you can see that at Stokes number 1, all the LES results are qualitatively the same, but just with varying magnitude, although in this case, ours is the worst performing. Then for Stokes number 5, we begin to see some discrepancies, particularly with no dispersion model, and there is quite a significant error in this intermediate part of the channel. So to summarize what we've done, we implemented a LES dispersion model in OpenFOAM. So currently, like I mentioned, there's only Reynolds averaged or dispersion models for Reynolds averaged fluid turbulence. This gave us improved predictions of concentration of inertial and tracer particles. And this bodes well for our future study where we will implement this in the realistic patient airways to model drug particle deposition. So finally, I'd like to thank Professor Marchioli, who provided the DNS data, as well as my funders, the Carnegie Trust. And I would just like to add that we plan, after we publish this study, to make the code available on GitHub for anyone that wants to use it.
Thank you, Josh. Glad we finally got that working.
Yeah,
I had some significant issues yesterday myself with connections, so I know how frustrating it can be.
Yeah.
It's very interesting work. Obviously, the application you begun the presentation with was a respiratory illness. Obviously, the reason we're remote at the moment is because of a supposedly airborne virus, right? It's so. Do you have any applications for this work in relation to COVID?
So when we're modeling COVID, it would be kind of more a ventilation in, say, a large room.
Correct, yeah.
So the Lagrangian approach probably wouldn't be best suited, but there are a lot of papers that use the same stochastic model, but for dispersion of a passive scalar. So that could be one way to implement this for improving ventilation.
I've been doing some work, experimental work in a local hospital here, looking at how high flow nasal oxygen therapy can lead to the spread of COVID. So there are certainly internal flows of interest too. So I wouldn't neglect it. So Richard Kenny is asking what is the key parameter in the Langevin model to ensure consistency with DNS results? Model.
So over the last couple of months, I've found that it really all comes down to this parameter G star, which is how easily it is for the model to relax back to the fluid. So if we overpredict that, then or underpredict it, then we get some significant spurious component. So to counteract that, this Innocenti paper just provided the first term in this equation. So just the ratio of subgrid dissipation to subgrid kinetic energy. But in this 2004 paper, they focus more on the wall modeling. So we include the resolved dissipation rate, as well as this extra half epsilon over K. And also this extra term in the equation for dx accounts for diffusion in space, which we found to improve our results in the boundary layer.
Thank you. And Anonymous has asked, says a nice talk, but wants to know if there's a published paper about this work. So obviously you've mentioned you're going to open source the code, but have you published a paper on this?
No, not yet. So I actually just managed to, we've had the inertial particle results for a while, and we've been dealing with this concentration of the tracer particles. I just managed to fix this a couple of weeks ago. So I'm going to move on to the airway simulations in the next couple of weeks, and hopefully we should have a preprint out in the next couple of months. So whoever that is, feel free to message me, and I can email you whenever there's anything released.
Fantastic. We have 6 seconds left according to the session. So I'd like to thank everyone for speaking and thank all our attendees. Thank you very much.
Thanks, Kevin.
Okay, and that's the end of the session. Thank you, everyone, and hopefully see you soon.